Assalamu alaikum, everyone. Today's discussion focuses on the mathematical description of a harmonic wave on a taut string. We will see how to determine the form of the wave function for a sinusoidal wave using both the sine and the cosine functions. So stick around, watch, and learn. Even though many characteristics of periodic waves can be described by using the concepts of wave speed, amplitude, period, frequency, and wavelength, more often than not, we need a more detailed description of the positions and motions of individual particles of the medium at particular times during the wave propagation. Specific examples are waves on a stretched string. If we ignore the sag of the string due to gravity, the equilibrium position of the string is along a straight line. We take this to be the x-axis of a coordinate system. Waves on a string are transverse. During wave motion, a particle with equilibrium position x is displaced some distance y in the direction perpendicular to the x-axis. And the value of y depends on which particle we are talking about. That is, y depends on x and also on the time t when we look at it. Thus, we say that y is a function of both x and t. And y quantity x t is what we call the wave function. Alright? It describes the wave. If we know this function for a particular wave motion, we can use it to find the displacement, alright, from the equilibrium of any particle at any time. So, we will be using two equations, alright, in determining the y displacement of any particle in the medium or for any value of x at any given time t. So the sine function is simply the product of the amplitude capital A multiplied by the sine value of the quantity kx minus omega t, and for the cosine function, all right, it's just the product of the amplitude capital A times the value of the cosine of the quantity kx minus omega t. So in both of these equations, the variables k is what we call the wave number, and the Greek letter omega is what we call the angular frequency. So in our succeeding discussion, okay, you will find out when to use the sine function and the cosine function. Let's take a look at our first question. Number one, a transverse wave on a taut string is represented with the wave function y quantity xt equals capital A sine quantity kx minus omega times t, and that is equal to 0.2 meters times the sine of 6.28 per meter times x minus 1.57 per second times the time t. Question is, find the amplitude, the wavelength, the period, and the speed of the wave. We have the waveform shown in the figure. We call this the snapshot of the string at time t equals 0. The wave function y, quantity xt, or y as a function of x and t, is just equal to the product of the amplitude of the wave, capital A, and the sine value of the quantity kx minus omega t, where k is called the wave number and omega is the angular frequency of the wave. The negative sign or minus sign in this formula signifies a wave that is moving towards the positive x-axis. Alright, so if the wave is moving towards the negative x-axis, this becomes plus. Alright, the sine function here is used because the left end of the string, that is x equals 0, is at the equilibrium position, y equals 0, and at time equals 0. Alright? So in the problem, we are given the wave function equal to 0.20 meters multiplied by sine quantity 6.28 per meter times x minus 1.57 per second times the time t. So based on this wave function equation, all right, the amplitude of the wave is understood to be equal to 0.20 meters. And the wave number k, all right, is equal to 6.28 per meter. While the angular frequency omega is equal to 1.57 radian per second. So the first target variable is the wavelength, lambda. And we can find the wavelength lambda by just dividing the value of 2 pi divided by the wave number k. The second variable or target variable is the wave's period, capital T, which is just equal to 2 pi divided by the angular frequency omega. And lastly, the other target variable, of course, is the speed of the wave propagation, small letter v. Right? It is just equal to the angular frequency omega divided by the wave number k. Moving on with our computations, for the wavelength lambda, we divide 2 pi by k, or 2 pi divided by 6.28 per meter, right? To get the value of lambda equal to 1.00 meter. The period, capital T, which is just equal to 2 pi divided by the angular frequency omega, or 2 pi divided by 1.57 radian per second, that is, capital T is equal to 4.00 second. Finally, for the wave speed, all right, which is just dividing the angular frequency omega by the wave number k, or 1.57 radian per second divided by 6.28 per meter. Doing our math, we will get, all right, the speed of the wave equal to 0.250 meters per second. Our last question, number 2. A sinusoidal wave with wavelength 0.400 meter travels along a string. The maximum transverse speed of a point on the string is 3.00 meter per second, and the maximum transverse acceleration is 8.50 raised to the fourth power meter per second squared. Question: what are the propagation speed v and the amplitude capital A of the wave? The figure shows also a snapshot of the taut string at time equals 0. The wave is moving from left to right. Now, supposing that the y displacement of a particle at the left end of the string, that is labeled here as particle A, which is located at x equals 0. All right? So, at x equals 0, this is where the wave originates. And particle A is at a maximum positive y displacement, where its transverse velocity is also equal to 0. Now, four other particles are also chosen. All right? Particle B, which is located at the equilibrium position and is at its greatest velocity directed upward. And we have particle C, located at the maximum negative displacement. So, its velocity is also equal to 0. And the other particle is particle D, right? And particle D is also located at the equilibrium position with a maximum downward velocity. And lastly, particle E is at the maximum positive displacement with, of course, 0 velocity. The acceleration of particles A, C, and E are represented here by the green vector arrow. So you will notice that for particle A, the direction of the acceleration, all right, is towards the equilibrium position. In other words, it is negative. All right, the maximum acceleration at point A, all right, or at the maximum positive displacement, the acceleration is negative. All right. Now for particle C, which is also at its maximum but negative displacement, its acceleration, which is also maximum, is directed also towards the equilibrium position, but it is directed upward. And particle E, which is located also at the maximum positive y displacement, its maximum acceleration is also directed in the negative direction towards the equilibrium position. All right? The two particles, B and D, are said to be uh, or have zero acceleration because these particles, since they are in the equilibrium position, that means the net force acting on them is equal to zero. All right. So the instantaneous acceleration of particles B and D are also equal to zero. Now the wave function y quantity xt is given here by the equation capital A cosine quantity kx minus omega t. All right. We are using the cosine function because if you notice, the left end of the string, which is represented by particle A, all right, happens to be at the maximum positive y displacement. All right. So uh, we can check. Earlier we said that the displacement of particle A is at its positive maximum displacement. So it is located exactly at the amplitude. All right, the displacement of particle A is exactly equal to the amplitude of the wave. All right, so we can check that by just substituting x equals 0 and time equals 0, and then determine what the value of y is. All right, so with x equals 0 and time equals 0, all right, we have uh, the value inside the parentheses equal to 0. Kx is 0, omega t is 0. And what is the cosine of 0 radian? Of course, it is equal to 1. So therefore, uh, we can say that the displacement of particle A is just equal to uh, the amplitude, capital A, times the cosine of 0 or 0 radian, which is equal to 1. Hence, the y displacement of particle A is just equal to the amplitude, capital A, of the wave. All right. So before we proceed to describing the velocity of each of these particles, we are emphasizing that the wave or periodic wave that we are talking about is a transverse wave. All right. Because the way the particles in the medium, which is the string, vibrate, it's vibrating or they are vibrating such that the direction of their transversal velocities are in fact perpendicular to the direction of the wave propagation. Hence, this type of periodic wave is known as transverse wave. All right. Now, also taken from the wave function equation, all right, the equation for determining the instantaneous transversal velocity, all right, can also be uh, expressed in this equation, all right. So b sub y, all right, as a function of x and time t is just equal to the product of the angular frequency omega, all right, the amplitude capital A, and the sine value of quantity kx minus omega t. Again, minus because we are still talking about the wave moving towards the positive x-axis. All right. So we can use this if we want to determine the transversal velocity of each particle, such as particle A. Once again, all right. All we have to do is substitute the value of x, all right, for particle A, x0 at time 0. So we will get as the transversal velocity of particle A, all right, equal to omega multiplied by the amplitude A and the sine of 0 radian, which we know is equal to 0. In short, the transversal velocity of particle A, all right, which is located at the maximum displacement or y displacement, all right, is equal to 0. So this verifies our earlier description that the instantaneous velocities, transversal velocities of a particle located at the maximum displacement is in fact equal to 0. All right, so that also is true for particles E and particle C. All right, and last but not the least is the equation for determining the transversal acceleration a sub y. All right, so for the transversal acceleration as a function of x and t, the formula is a sub y equals the negative of the square of the angular frequency, omega squared, multiplied by the amplitude, capital A, and the cosine of the quantity kx minus omega t. All right? And earlier we said that the acceleration of such particles like particle A, particle E, all right, they are both located at the positive maximum y displacement. We said that the acceleration, the magnitude of the acceleration is in fact maximum, but it has a negative sign, all right? The acceleration is always in the opposite direction as the displacement or the amplitude. All right. So since the displacement of particle A and particle E are both positive, so their instantaneous acceleration must be negative. All right. And using this formula, we can verify if that is true. Again, we just substitute the value of x equals 0 and the time equals 0 in our equation. All right. So this is what happens. A sub y becomes negative omega squared multiplied by the amplitude, capital A, and the cosine of the angle 0. All right. If x and t are equal to 0. So the quantity inside the parentheses earlier will all become 0. And the cosine of 0 radian, of course, is equal to 1. That means, all right, the acceleration a sub y is just equal to negative omega squared multiplied by the amplitude, capital A. So our description earlier agrees with our mathematical computation that the instantaneous acceleration will always be in the opposite direction as the displacement, all right, or the maximum displacement. Here are the given data. The wavelength lambda is equal to 0.400 meters. The maximum transversal velocity of the particle v sub y max is equal to 3.00 meters per second. And we also have the maximum transverse acceleration a sub y max equal to 8.50 raised to the fourth power meters per second squared. The target variables are the speed of the wave propagation, denoted by small letter v, and the wave's amplitude, denoted by capital A. We make use of the quantity k, known as the wave number, which is equal to 2 pi over the wavelength lambda. And since lambda is given, we find k, all right, equals 2 pi divided by 0.400 meter, or the wave number k is equal to 15.7 radians per meter. The angular frequency omega is also equal to the product of the wave number k and the speed of the wave propagation. That is, omega equals k times v. Hence, we can also express omega in terms of the wave speed v, all right? That is, omega is equal to 15.7 radians per meter multiplied by v. V is one of our target variables. Earlier, we already said that the wave number k is equal to 15.7 radian per meter. We can find the angular frequency omega in terms of the wave number k and the wave speed of propagation, small letter v. So, the angular frequency omega is just equal to k times v. All right? So substituting the value of k, we'll get omega equals 15.7 radian per meter multiplied by small letter v, or the speed of the wave propagation. All right? This formula for relating the angular frequency and the speed of the wave propagation, all right, is true for any periodic motion, all right, such as what we are discussing now. Now, when a particle is at the equilibrium position, all right, its v sub y is said to be maximum, all right? And the formula for v sub y max in terms of omega and a is this, all right? V sub y max is simply equal to the product of the angular frequency omega and the wave's amplitude, all right? Because earlier we noted that if a particle is located in the equilibrium position, then we say that its vertical displacement is zero, all right? So, at the equilibrium position, okay, the transverse velocity of any particle, okay, within the string, okay, is considered maximum. All right? And this can be equated. All right? The b sub y max can be equated to the wave number k multiplied by the speed of wave propagation and the amplitude capital A. All right? And since our target variable or variables are v and the amplitude A, all right, we will isolate capital A or the amplitude of the wave and come up with this first equation or equation number 1. All right? We are given the maximum v sub y equal to 3.00 meters per second. And that will be divided by the product, all right, of the angular frequency omega, which we express as 15.7 radians per meter multiplied by small letter v, or the speed propagation, all right, of the wave. So, equation 1 contains two unknown variables, the amplitude capital A and the wave speed of propagation small letter v. All right. Also, we are given the maximum transverse acceleration a sub y max. All right. So, a sub y max is the acceleration of any particle that has a displacement equal to the amplitude of the wave. All right. And a sub y max, or the transverse acceleration of any particle located at the maximum displacement, is related to the angular frequency omega and the amplitude A in this equation. So a sub y max is just equal to the square of omega multiplied by the amplitude A. Again, we can express this in terms of the wave number k, all right, as well as v, the wave speed of propagation. That is, a sub y max is also equal to negative k squared v squared multiplied by the wave's amplitude capital A. And again, we can isolate the amplitude capital A, all right, for us to come up with equation number 2. So, with amplitude A isolated, that can be expressed as the what we call the acceleration, that is given as 8.50 raised to the 4th power meter per second squared. All right, and that will be divided by, all right, the square of the value of k multiplied by the square of the speed small letter v. Okay, we already discarded the negative sign. Okay, when we substitute the square value of k in this formula, okay, we disregarded it because the only purpose of the negative sign in this formula is that we want to emphasize that the acceleration a sub y, all right, always has the opposite direction of the displacement. So when we're talking about a positive a sub y, it follows that the displacement is negative a, or that the amplitude that we are referring to is the one that is in the negative or maximum negative displacement. All right. So since we're only after the magnitude of the amplitude, all right, strictly speaking, amplitude is always positive. So that's the reason why we already ignored the negative sign here. So once again, these are the two equations, equation 1 and equation 2. In just a short while, we are going to determine these two unknown variables, all right, or target variables, uh, capital A, or the amplitude of the wave, and the wave speed, small letter v, wave speed propagation. Equating these two equations, 1 and 2, we will have uh, the following, all right? So in the first equation, we have 3.00 meter per second divided by 15.7 radian per meter, okay, multiplied by the speed v. That's equated to equation number 2, 8.50 times 10 to the 4th meters per second squared divided by uh, the square of 15.7 radian per meter, all right, and multiplied to the square of the unknown variable v. And simplifying, all right, so this is the simplified equation now, and eventually we will get the value for the wave speed of propagation, small letter v, which is equal to 1.80 raised to the third power meters per second. Take note that we followed the rules significant figures in our operation. To find the wave amplitude, we use this equation, equation number 1, and we just substitute the computed value for the speed of wave propagation, small letter v. All right. So the value of a computed value of small letter v is 1.80 times 10 to the third power meter per second. All right. So doing our math to find the amplitude, capital A, we get the amplitude equal to 1.06 times 10 to the negative 4 meters. All right. So this is the amplitude of the wave. Again, we followed the rules of significant figures. Now for our evaluation, okay, we can actually check if our computed amplitude, capital A, will come out the same as this, okay, by using equation number 2. All right, this is equation number 2. So all we need to do is also substitute the computed value for the speed of the wave propagation, v. That is, all right, um, this is the value of the a sub y, or the transverse acceleration, all right, and that will be divided by the square of 15.7 radian per meter, which is in fact 246.5 meters per meter squared, and also the square of the computed speed of the wave propagation. Okay, the square of 1.80 raised to the third power meter per second is of course 3.24 times 10 to the sixth power meter squared per second squared. Alright, so simplifying this, we get the same value for the amplitude, equal to 1.06 times 10 to the negative 4 meters. And that concludes our tutorial. Till the next episode, inshallah. Thank you very much for watching. Please follow me in my FB page, and please don't forget to subscribe to my YouTube channel.